In geomorphology, we study topography, and so topographic maps are really at the center of our science. This example here shows the United States of America with some different colors for different elevations. So for example, we have these greens in the lowlands, we have these brownish colors as you get a little bit higher, and then as the elevation increases dramatically, it changes to these brighter white colors. And this is the kind of map that simulates vegetation with changing elevation by making us remember that green areas are often low, brown areas are often higher, but of course that's not always the case. In any case, topography is a very important part of our world, and so we're going to go over the basics of how topographic maps are created and how to read them. So we talked a little bit earlier about the etymology of geomorphology, with the geo part pertaining to the earth, the morph being its shape, and the logy, or ology, being the study of. So it's the study of the shape of the earth. And since topographic maps provide the literal shape of Earth's surface, they're really at the core of our field. So topographic maps have a large number of features, and we're using this example that I have on the slide at the right of the area around El Dorado Springs, or the El Dorado Springs Quadrangle in Colorado. And this is giving us some amount of information on the physiography, the topography at that place. And so what we have to think about is what coordinate system is it in. So there's a datum and a projection. We'll get into those. What is the scale of the map? What does the legend look like? So how do you interpret all the symbols? What do these lines on the map mean, and how do they help you understand the elevation? And then also some information about the publication, which can tell you about when it was made and what the location is. So just to start out, the coordinate system is right down here. It says National Geodetic Vertical Datum of 1929. So this is something that's telling us where we put the zero marker, so where we project sea level underneath the continents, and where we decide that we're going to say, okay, this is zero elevation versus, this is a much higher elevation. And since this is a map in the US, these are in feet, so we see things like 6,400 or 6,800 feet. So, but there is a good question, right? So if you're in Colorado or Minnesota or Nebraska, how do you know how high you are above sea level, right? What is actually sea level? What's sea level at that point, right? If you're in coastal California, it's really easy to see where sea level is because you can be standing on a sea cliff and looking down and it's like, oh, yep, I'm higher than that. But if you're off in, Nebraska, you don't really have that point of reference. So what we do is we create a surface that we call zero. And that can be one of a couple things. So one option is to use something called the geoid, and that's the gravitational equipotential surface. And what that means is that gravitational force is equal at all places on that surface. And so what you could imagine then is that if there were a mass of water that went a little bit higher than that surface, it would have higher potential, right? And so it would actually be, sitting above the rest of the water body, and then that water would deform and it would flow back down to the surface. And likewise, if you made a hole in the surface, then in order for the water body to move back up to it, that mass would move back into the hole and fill it up. And the idea, therefore, is that because water deforms so easily, the pressure forces inside water are capable of moving it laterally to balance out forces of gravity, and therefore, water will follow a single surface where the gravitational potential is equal everywhere. And we choose this very conveniently to be equal to global mean sea level. So the geoid is one way of having a datum, and ellipsoid is another way. And so an ellipsoid is just taking, we think about the spherical Earth approximation like a globe, and Earth is actually a little bit fat about the middle. And so squish that globe down, and that's an ellipsoid. And so it is a uniaxial shape, by which I mean that if you put an axis through its north and south poles, it is symmetrical about that axis, but it is not going to be symmetrical about an axis placed between, an arbitrary point on the equator and an arbitrary point exactly opposite the that first point on the equator. And so this is another way that we more simply approximate the shape of Earth. And this is exactly what I'm talking about there. So on the left-hand side, you can see that there's a sphere, and we have this A and B, which are the two different axes along the sphere. And so in a sphere, A and B are equal. In an ellipsoid, which is what Earth is, B and A are not quite equal. And this, if you can write this fraction, A minus B over A, so that basically is going to say the longer axis minus the shorter axis, quantity over the longer axis. That's going to give you a ratio, which we call the flattening. And the flattening of Earth is, incidentally, about factor of 1 in 293. So why is Earth not quite a sphere? So we have gravitational force that's the same in all directions. And so, in fact, Earth is round, as are many planetary bodies, because it's actually collapsing under its own mass. And the sphere is the most energetically favorable form. If there was something much higher, then it would start to fall down and eventually form into the same spherical shape. But the Earth is rotating as well, and so there is a centrifugal force pushing outwards, and that is pushing outwards the very most along Earth's equator. And so Earth's shape is really a combination of a battle or balance between the gravitational force pulling everything together and the centrifugal force pushing the equator outwards. And as a result, the middle bulges out because some of the centrifugal force, or all of the centrifugal force rather, acts to oppose some of the gravitational force, thereby canceling it out. And so this is just a little physics aside, especially if we have any physics majors in the room, because at least, when I took introductory physics, or perhaps when many of you took introductory physics, centrifugal forces were kind of laughed at. We talk about centrifugal forces when we're on the merry-go-round as kids, but in physics class we learn that they don't exist, that they're fictitious forces. But they do, as a matter of fact. So on the right-hand side is a XKCD comic, one of the first ones I'd ever read. And so the villain says, "How do you like my centrifuge, Mr. Bond? When I throw this lever, you will feel centrifugal force crush every bone in your body." And our poor hero says, "You mean centripetal force? There's no such thing as centrifugal force." To which the villain says, and by the way, many villains in movies are always Dr. something. I mean, think about right, like Dr. No, Dr. Evil, Dr. Moriarty. Anyway, if you get a PhD, your chance of being the villain over the hero increases dramatically. Continuing on, though, he says, "A laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simply construct Newton's laws in a rotating system, and you will see a centrifugal force term appear as plain as day." And that's true. So Earth is a rotating system, right? So we're actually on a rotating reference frame. And so with respect to us, and with respect to Earth itself, that centrifugal force is actually pulling out its midsection in exactly the same way as it was if you were on a merry-go-round as a kid and were holding on for dear life, trying not to fly off as your much larger friend pushed you around in circles. And so the hero says, "Come now, do you really expect me to do coordinate substitution in my head while strapped to a centrifuge?" Which is a reasonable request, right? Because at least you might want a pen and paper. And the villain says, "No, Mr. Bond, I expect you to die," which makes him quite a bad doctor because you'd hope that he would at least want his student to learn. So, pardon. So, from outside of the Earth, we would see that there's a centripetal force, in fact, because if we weren't on Earth, what we would see is that the equatorial bulge or the equator of the Earth were constantly being pulled back in towards the center of the planet in order to not go spinning away. But from our point of view, we actually experience the centrifugal force pushing us outwards. And so it depends on where you are and what whether you're stationary or whether you're actually rotating. So on the same physics aside, gravity is actually lower at the equator than at the poles. And we can think about that because if Earth is a little bit flatter, so at the equator, you're farther from the center of the Earth. And we remember from Newton's laws of gravitation that if you're farther from a mass, that your gravitational pull, the gravitational pull that mass will have on you is less. And so if you're farther from the point mass in the center of Earth, at which we can approximate all of Earth's gravity to be emanating from because of Earth's symmetry. So if you're farther from that, like on the equator, you actually are truly lighter. Whereas if you're closer at the poles, you're a little bit heavier. And here in Minnesota, we're almost exactly at 45 degrees north. And we do many things here in moderation. We also do our gravity in moderation. And so if we do think about this, though, if you guys are, fans of Jimmy Buffett, we can remember that actually things are a little bit easier in paradise on the equator. Every single step that you take takes 1 part in 200 less energy, and you get a little bit of spring in your step. You get a little bit more motion. And so if you ever end up traveling to the equator, just remember that life is in fact truly easier, and your worries are a little bit lighter. But back to Colorado and topographic maps. So that's the datum, geoid or ellipsoid, and that determines, what approximation you're using for the shape of the Earth. In addition to that, and by the way, I just realized I wrote this in the lower right. So the National Geodetic Vertical Datum of 1929 is based on surveys and tide gauges, and tide gauges are stations that measure sea level all around the world. But the next thing is the projection. So we have around Earth being projected onto a flat map. So how do we do that? We have to distort it in some way because you can't actually take the shell off of a sphere and push it to be flat without wrinkling it or tearing it in some way. And so I've put a box around this little 474. We're gonna look at that and see what it means. So map projections are this way of representing an almost sphere, but let's just think about it as a sphere because that's a little bit easier onto a flat map. And so you can think about it, in this image, we have the one on the left, which is just taking a flat plane and thinking about how that will project. And you can see how that's shown. The North Pole is going to look perfect, but stuff at the equator is all just going to circumscribe one line at the very outside. And everything from about 45 degrees down and farther south, 45 north and farther south, is going to be really distorted and crammed into a small area. A cone or a cylinder is actually, in many ways, a really nice shape because those have one round dimension, and so they can actually conform a little bit better to the sphere. And so many projections are conical or cylindrical. And so this first projection that we're talking about is called an azimuthal projection, where we just have this sort of flat plane, and this is an idea of what it might look like. Conical projections in the middle look something like this, where you can see that you can actually show the whole world or a large fraction of the world. This is conical based in the northern hemisphere, so there's a lot of distortion and missing stuff in the southern hemisphere, but still, if you look at something like North America, Europe, or the northern parts of Asia here, it's not so bad. And then the cylindrical projection is like this. And so what you can see is that in the cylindrical projection, which is touching the equator, Africa actually looks pretty nice. It looks kind of like its natural shape. And Greenland looks bigger than Africa probably because, I think it is bigger than Africa because it's being stretched out so much at the poles. And you can actually see that if you shoot imaginary lines going horizontally out from the North Pole at this, anything that's at that towards the North Pole is actually going to be stretched and elongated on this mapping surface. So how do we pick the best projection? Many map projections are good in one area but distort the shape in the others. And there's no single map projection system that's the best everywhere. And so Over here, for example, on the right-hand side, these circles, which should be perfectly circle and perfectly the same size everywhere, are showing you this distortion. So we have something like this Mercator, this cylindrical projection on the right, on the top, and then we have another projection on the bottom, which is your kind of school classroom projection, which shows how different areas can be distorted with that as well. So no single projection will actually take you through the entire world and be able to represent everything perfectly, but maybe we can start to approximate small areas on Earth's surface using a projection, and maybe there's a system of projections that all will provide roughly similar answers. And the reason we think we might be able to do this, if you remember from math classes, something called Taylor series expansions, it's that any curve that we create can be approximated by a polynomial, and you can even use a very low order polynomial, so even like a constant or a straight line over some small or short distance. And so that concept translates directly here, and so maybe we can even use a flat or gently curving surface that might not be curving in both directions, that can be unrolled, to approximate the sphere, and it's going to work. So for that system, we use what's called the Universal Transverse Mercator Coordinate System. And it divides the world into localized strips that each use the same projection, and it minimizes distortion as a result. It's used by geologists, surveyors, and military archaeologists, hikers. Basically, this is the most common coordinate system that you'll see, other than straight latitude-longitude without a projection. So that's why I'm focusing on it, because we're trying for cost benefit here. And the Mercator projection is a cylindrical projection like I was showing you a couple slides ago, where it's a projection about the equator, right? So the cylinder is touching the equator. Here, it's a transverse Mercator system, so it's rotated 90 degrees. That's what the transverse part means. And it then is made to touch each of the lines of latitude, so each of what we call the meridians. And there are, in fact, different zones where we rotate that cylinder slightly, so it's touching a different meridian. And each of these 60 different UTM zones, so you can think 60 zones, 360 degrees, 360 divided by 60 is 6. So each of these zones is 6 degrees apart, is 6 degrees wide, and each of the UTM zones then corresponds to one of these positions for that cylinder on its side as it's being rotated about and touching Earth. What do these UTM coordinates look like? Well, they look like a set of meters, which is fantastic and very useful because now we don't have to worry about latitude and longitude. We can actually think about real units of length that we can measure or pace out on the ground. So the first number is the UTM zone, and so that in this case is 10 south. So we're looking at something in the southern hemisphere. The second number is the easting, and you can think of easting as the as the x coordinate. And the reason we use east instead of west is because then we have a coordinate system in which we're going positive to the right. That's just like the coordinate axes that you draw in algebra. The north, you can think about that like your y-coordinate axis back when you were in school in algebra. And that is showing you the numbers of meters north of a particular point. In the northern hemisphere, that's north of the intersection between the meridian that you're following and the equator. In the southern hemisphere, it's meters north of the South Pole. So the other thing that's interesting is you see over here, we just have these small numbers, right? These 832 meters, 683 meters, and it's dropping off these larger numbers, which we're actually observing exist on the coordinate axes. And they're written in a way where you have a little number or two, a couple big numbers and a few small numbers. And that's a really common way that this font is created because then you can count off kilometers very easily. So UTM zones of the USA. In Minnesota, we are very lucky that we're mostly in UTM zone 15, especially if you're in the eastern part of the state. Super duper convenient. If you're in Wisconsin, you're bisected into two different UTM zones, that's less convenient. If you're in western Minnesota, you're also bisected into two zones. If you're in Colorado, you're also mostly good. So it just kind of depends. If you're on the line between these two zones, sometimes you have to look at multiple maps projected in different ways. But just cross your fingers, hope you're lucky, and hope you're smack dab in the middle of one of these UTM zones. So that's our projection. After that, we look at the map scale. And right here it says scale is 1 to 2400. Great. 1 of what to 2400 or 24,000 of what? That doesn't really matter, right? So it could be 1 of my pinky nails on the map is going to be equal to 24,000 of my pinky nails lined up right next to each other in the real world. Or, 1 millimeter on the map is going to equal 2.4 kilometers in the real world. Or sorry, 24 meters. So that's the way that you can then compare the what you're measuring on the map with what you're measuring in the real world. Of course, you might actually just want to do that with something that you can actually line up a ruler to or a piece of string. And that's what this actual scale down here is for. And so what you could do, for example, if you're trying to take a hike and create a path, is take like a string, or failing that, take off your shoe, use your shoelace. And if you don't have a different piece of string, make that go along the exact path you want, because you can deform it. And then when you take it off the map, you can pull it tight, and then you can measure it up against that scale and figure out how long that should be. And along with that scale, they have this thing called the contour interval, and that means there's 40 feet of vertical elevation change between the lines that we've seen on the map. We'll talk about contour lines shortly. So the next piece of the legend, I don't have this here because it's actually quite large. Here is a legend that's pretty common to maps created by the U.S. Geological Survey. And so you see that there's this index contour, this bold contour, and typically every fifth contour is this index contour, and then there's the supplementary ones. There are zones of like cut and fill, so land alteration, mine dumps, dunes, sands, glaciers, streams, woodlands, scrublands, aqueducts. There's all sorts of information. One important thing is that this depression contours in the upper right, if you see those hatch lines going in, it means that those contours are actually pointing into an internally drained low area. And as you can see, these markings are related to topography, land use, hydrology, and land cover. Land cover meaning, what kind of plants or other things are there. Map legends can also include human-built facilities and features. So we have things like different kinds of roads, different kinds of surface features, different kinds of alterations we've made to the land surface. And so legends are great because you can read them, you see the symbol, you read what it is, you look for it on the map, and there you go. Not too hard. Geologic map legends will have some other information on them. I'm realizing this is a little bit fuzzy here, but you can see that there are different colors relating to different rock types. There are different symbols for different faults and folds and structures. And so you might actually, on your maps as a geomorphologist, if you're working in tectonic geomorphology or trying to understand relationships between geology and surface processes, you might also be looking at geologic maps. So there we are. So we can see the contour lines in this figure, and we can see that there are zones that are higher, so where you have Flagstaff Mountain represented right here, and zones that are lower. And so you see that then over towards the left, there's Lost Gulch. And also of some possible interest to those of us in geomorphology, you can see towards the upper left, there's this thing that says gauging stay. That's a USGS stream gauging station where they're measuring the amount of discharge in the river. That's something that geomorphologists often work on, is trying to establish and maintain these gauging stations. And the 5828 there is giving you the elevation of that gauging station also in feet. So contour lines, just to understand them, they're lines of equal elevation. So if you are going up a gentle slope, you're going to intersect fewer of these lines of equal elevation for a given lateral distance. And so, as a result, you're going to see the lines be spaced farther apart on the map. If it's much steeper, those lines are going to be much closer on the map. And that can help you to figure out what the slope is and whether it's a good way to walk somewhere or not, or even give you a general idea of what the profile of a river channel looks like. Is this a steep river that maybe is, cutting through bedrock, or is it a very gentle river that might just be moving sand and mud? And here's another example that I find to be quite useful. And this example right here is just showing what it looks like in this 3D perspective view. So, rules of contour lines. First off, contour lines can't touch across, because this means that two elevations would coexist, and that is just not going to be happening, right? Well, you can imagine some cases in which that might occur. If, for example, if there's a cave underneath some high topography. But that's a big point about these topographic maps. They're two-dimensional surface maps. So they're showing you the surface with the features of the land, of the elevations drawn onto them. But they're not actually able to show you the three-dimensional structure of, what exists below the land surface. Second is contour lines get closer together as the terrain gets steeper, and that's what we just talked about. And you can actually then measure the distance between the contour lines and combine that with some knowledge that you have about the lateral distance, maybe from reading the map scale. And then you can use rise over run to get slope. And the third thing is the rule of V's. So that we say that contour lines V up valleys, and that's because we have lower topography as we're entering high ground. And then contour lines V outwards along ridges where we have this locally high terrain. Those words aren't so helpful. Let's just look at it. So first off, spacing and steepness, what we can see on the steep slope, especially as you look between the 1716, 1840 feet contours, that bold line towards the top and the line right next to it on the left-hand side, which is typically the west side, are very close together. Meanwhile, on the gentle slope, they're far apart. So we got that. We looked at that before. Let's move on to these V's. What am I talking about? So if you look up this valley, what you can see is that the contour lines are kind of bending around, and they're bending around up the valley, such that there's then a point in the V, and we have a couple V's underneath the A and the L in valley, and then they go back out around the next ridge. And so you can see these contour lines actually moving up the valley. And what that means is that this contour line that's representing much lower topography is following that low topography in the river valley zone, which is lower, and then going back out to show that that same elevation point is actually much farther downstream if we end up going kind of climbing up onto the ridge. The ridges have these V outwards, and what I mean by that then is that you can see the ridge contour lines are creating this symbol of a promontory where we have this high topography that juts out into the surrounding landscape. And there are a lot of resources on the internet about rules of V's, so if that doesn't make sense to you, go ahead and evaluate yourselves of one of those. Finally, there's some publication data. So this is the Eldorado Springs Quadrangle. It has some information about where it is, and it also is telling us that it complies with national map accuracy standards. It's from the U.S. Geological Survey in Denver, Colorado, and that you can also get a folder describing topographic maps and symbols. So, with that is our introduction to topographic maps. And these maps are something that we use in geomorphology almost all the time.